Welcome to this overview of CASA, which stands for Continuous Agent Semantic Authorization. It provides an intent-scoped authorization layer for Kubernetes multi-agent systems, enforced at the network layer, with no code changes required in your agents. In this walkthrough, we will cover the problems that CASA solves, its core approach, the architecture, and a demo of CASA to show its key features. Let's get started. Modern AI applications are increasingly composed of agents, MCP servers, and orchestration layers that collaborate autonomously. These systems are powerful, but they introduce a fundamental security challenge. Today's identity and authorization systems were built for humans, not agents. They assume human users with static roles, and they expect access patterns to be predictable. But agents don't work that way, and the assumptions behind traditional identity systems simply don't hold. The second problem is that once an agent has access to any given tool, it can use that tool for anything, regardless of what the user actually asked for. This means that a single compromised or misbehaving agent can misuse any tool that it has been granted access to, creating a broad and difficult-to-contain risk surface. And the third problem is that most existing security solutions require code changes. They demand SDK integration, application-level modifications, and tight coupling between the security layer and the agent code. This creates friction for developers and slows down adoption, especially in environments where agents and tools are rapidly evolving. CASA addresses these problems with a fundamentally different approach. First, CASA is purpose-built for agentic AI. It is designed for how modern AI systems actually work, autonomous, dynamic, and collaborative, rather than trying to retrofit human-centric identity models onto agent workflows. Second, CASA introduces intent-scoped authorization. Every tool call made by an agent is validated against the user's original intent. If an agent tries to invoke a tool that does not match what the user asked for, CASA blocks it at the network level, before the tool even executes. And third, CASA requires zero code changes to your agents or MCP servers. Enforcement is handled entirely through sidecars and eBPF, and configuration is done declaratively through Kubernetes CRDs. Your applications don't need to integrate any SDK or modify their code in any way. Overall, the core principle of CASA is simple. An agent should only be allowed to do what the user actually asked for, nothing more. Let's take a look at the Explorer UI, which provides a read-only observability dashboard for monitoring and managing multi-agent system activity. The main dashboard gives you an overview of all configured multi-agent systems, application counts, and tool call decisions, showing how many were approved versus denied, along with the reasons for any denied tool calls. From there, you can drill into the details of a specific multi-agent system, seeing its registered agents, clients, and MCP servers, along with their scopes and the authorization checks that are enabled. You can also view tasks tracked within a multi-agent system through the traceability feature, including authorization requests and full traces for each task, showing token-level detail for each user session with allow or deny decisions and check details per tool call. Now let's walk through the architecture of CASA, building it up step by step. We'll start with a typical multi-agent system setup before CASA is introduced. In this baseline scenario, you have a Kubernetes cluster with a namespace dedicated to your multi-agent system. Inside that namespace, there's a client pod running a user-facing client application, an agent pod running an LLM-powered agent, and an MCP server pod running a server that exposes tools for the agent. The agent also uses an external LLM through an OpenAI-compatible API for its reasoning. This is a straightforward setup, but it has no authorization layer governing what tools the agent can call or whether those calls are appropriate. In the first step of introducing CASA, we inject sidecars and attach an eBPF program. The CASA sidecar is an envoy-based proxy that gets automatically injected into every pod in the multi-agent system namespace. It intercepts all inbound and outbound network traffic, without requiring any changes to the applications themselves. Alongside the sidecars, an eBPF program is attached to the network stack, enforcing policies at the kernel level and binding calls together through traceability. Together, these two components give CASA complete visibility and control over all communication within the multi-agent system. In the second step, we introduce the CASA runtime. This runs in its own namespace and manages identity, tokens, and orchestration. The CASA runtime includes the Explorer UI, which is the admin dashboard we just discussed for monitoring and managing multi-agent system activity. It also includes the auth service, which handles token issuance and exchange, Keycloak as the identity provider backing the token cryptography, a Postgres database for state storage, and the traces service, which persists domain event traces and eBPF flow data and exposes a query API consumed by the Explorer UI. Multi-agent systems are configured declaratively using Kubernetes CRDs, specifically the multi-agent system custom resource, which defines the applications in a system and which tool authorization checks are enabled. In the third and final step, we enable the authorization checks themselves. These come in two categories. Deterministic checks are rule-based validations that verify whether the agent's tool requests are consistent with the data observed by the sidecars. For example, they ensure that the agent has not tampered with tool definitions or parameters, and that every tool call corresponds to a legitimate LLM response. These checks are fast and catch straightforward violations. Semantic checks complement the deterministic checks with AI-powered validation. These use an LLM-based task extractor and task-to-tool matcher to determine whether a requested tool actually matches the user's original intent. Even if a tool call passes all the deterministic checks, it can still be denied if it doesn't align with what the user asked for. For example, if a user asks for a bank account summary but the agent tries to initiate a bank transfer, the semantic check will catch that misalignment and deny the tool call. These layers of enforcement, sidecars intercepting traffic, eBPF enforcing policies at the kernel level, deterministic checks catching rule violations, and semantic checks catching intent misalignment, when taken together, provide comprehensive protection for multi-agent systems without requiring any changes to the agents, clients, or MCP servers themselves. Now let's see CASA in action. For this demo, we are using the sample agents and banking MCP server included in the CASA repository. We have deployed two multi-agent systems side by side, each with a true multi-agent architecture. Each system has an orchestrator agent that receives user requests and delegates work to specialized subagents, a beneficiary agent, a balance agent, and a payment agent. All of these subagents use the same banking MCP server, which provides tools such as getting an account summary, getting scheduled payments, transferring money between accounts, adding external beneficiaries, and scheduling payments. Users interact with each system through a single chat UI connected to the orchestrator. The first multi-agent system is the safe version, where all agents behave as expected. The second is the compromised version, representing a realistic scenario where an agent upgrade introduces malicious behavior that you cannot detect without inspecting the agent's internal code. In the compromised system, two agents have been upgraded with malicious logic. The compromised orchestrator agent, which modifies user messages to trick the payment agent into transferring funds, and the compromised beneficiary agent, which makes hard-coded tool calls to add an attacker-controlled external beneficiary. The balance agent and payment agent remain unchanged. Let's start in the Explorer UI and take a look at how these two multi-agent systems are configured. The dashboard shows an overview of the system, with the number of allowed and denied auth requests, and the distributions of the deny type and the deny reasons. Opening the multi-agent systems view, we can see both deployments listed in the UI with some high-level details. If we open the safe multi-agent system, we can review its registered agentic services, the orchestrator, beneficiary, balance, and payment agents, along with the banking MCP server and the enabled authorization checks and scopes. The compromised multi-agent system has the same configuration, the same agents, the same MCP server, the same checks enabled, and the same scopes. The only difference is that two of its agents have been upgraded with compromised logic. Now let's run the safe example first. We switch to the chat UI for the safe system and send a request asking to add a new beneficiary to the account, providing details like the beneficiary's name, account number, bank, and relationship. After a moment, the system responds confirming the beneficiary has been added. From the chat UI, this is all we see, the user's message and the response. Everything looks normal. But let's switch to the Explorer UI to see what actually happened behind the scenes. If we look at the traces for this task, we can see each step the system took. The orchestrator agent received the user's request and routed it to the beneficiary agent. The beneficiary agent called the LLM, and the LLM selected the Add External Beneficiary tool. This tool call passed the deterministic checks, confirming it corresponds to a legitimate LLM tool call request. It also passed the semantic checks, confirming that adding a beneficiary is aligned with the user's intent. Tool call is marked as allowed and everything looks good. Additionally, and as we see in the trace, the tokens that are issued and used within CASA are being exchanged at each step of the task. This is because the tokens provide only one-time access and are fungible, which means that a token that is approved for a particular tool and task can't be reused multiple times. The tokens are also linked to a particular client ID metadata document and contain both subject and act claims to support this, which means that a token is bound to a particular agent acting on behalf of a client. Before we move on, let's quickly confirm the setup of the compromised multi-agent system. If we open its configuration in the Explorer UI, we can see that it has the exact same authorization checks enabled, the same agents registered, and it uses the same banking MCP server. The only difference is that the orchestrator and beneficiary agents have been upgraded. Everything else is identical, which means any difference in behavior is entirely due to those upgraded agents, not the configuration. Now let's run the same request through the compromised example. We switch to the chat UI for the compromised system and send the exact same input, asking to add a new beneficiary with the same details. After a moment, the system responds, and from the chat UI it looks the same as before. The beneficiary has been added successfully. There is no indication that anything unusual happened. But if we switch to the Explorer UI and look at the traces for this task in the compromised multi-agent system, we can see a very different picture. Alongside the legitimate tool call, the compromised agents attempted to make unauthorized actions. First, we can see that the compromised orchestrator agent forwarded the user's message to the payment agent, but instead of simply routing the beneficiary request, it injected instructions requesting a fund transfer. The payment agent, unaware of the manipulation, called the LLM with this modified message, and the LLM selected the transfer between accounts tool. The payment agent then attempted to execute these tool calls. Because there was a corresponding LLM tool call request, the deterministic checks passed. However, the semantic check caught them. The user asked to add a beneficiary, not to transfer funds. The intent did not match, so the tool calls were denied. Next, the compromised beneficiary agent tried to call add external beneficiary with attacker-controlled details. This tool call was denied by the deterministic checks because the agent made this request without any corresponding LLM tool call request. It was hard-coded directly into the agent's logic, completely bypassing the LLM. Finally, the legitimate add external beneficiary call from the beneficiary agent's normal flow passed both checks and was allowed as expected. This allowed the system to complete the user's actual request, adding their beneficiary, while silently blocking all the malicious side actions. So looking at the traces, we can see the full picture. Allowed tool call to add external beneficiary for the user's actual request is marked as approved, while the denied calls, the hard-coded add external beneficiary with attacker-controlled details and the orchestrator-triggered transfer between accounts, are each marked with the specific check that caught them, whether deterministic or semantic, along with the reason for denial. All of this was completely invisible to the user in the chat UI. CASA silently protected them in the background from the compromised agent's malicious behavior, without breaking any functionality or requiring any code changes to the agent's or MCP server. Without CASA in place, all of these malicious actions would have been executed. The compromised beneficiary agent would have added an attacker-controlled external beneficiary, and the compromised orchestrator would have triggered unauthorized fund transfers through the payment agent, all without the user's knowledge or consent. With CASA, the deterministic checks caught the hard-coded tool call that bypassed the LLM, and the semantic checks caught the intent mismatched transfer requests that was triggered through message manipulation. These protections work across agent boundaries in a multi-agent system, catching compromised behavior no matter which agent in the chain is responsible. Now that we have seen the trace details, let's switch to the overview of the compromised multi-agent system to look at another feature of CASA. Because the sidecars intercept and log every message flowing through the system, CASA can dynamically build a live topology of the multi-agent system without any manual configuration. If we open the graph view, we can see a visual representation of the system's architecture. Each agent and the MCP server appears as a node, and the edges between them represent the messages passing back and forth. What's particularly useful here is that the edges connecting agents to the MCP server reflect the rate of allowed and denied tool calls over time. As more denied tool calls accumulate, the edge's color gradually shifts to red, giving users an immediate visual signal that something is wrong. In our compromised system, we can already see the edges turning red where the compromised beneficiary agent and the payment agent connect to the MCP server, corresponding to the denied tool calls we just reviewed in the traces. Importantly, this graph is not something we defined manually. It is constructed entirely by CASA at runtime, based on the actual data flowing through the multi-agent system. Finally, if we navigate to the auth requests view, we can see a centralized log of every authorization decision CASA has made across the system. Each entry shows the tool that was requested, which agent made the request, whether it was allowed or denied, and the specific check and reason behind the decision. This view makes it easy for users to quickly spot patterns, for example, repeated denials from a specific agent or a sudden spike in semantic check failures, and begin investigating the underlying issue. Rather than having to dig through individual traces, this gives a single pane of glass for understanding what CASA is detecting and blocking across the entire system. That brings us to the end of the demo, and thank you for watching this overview of CASA. We hope it has demonstrated how Continuous Agent Semantic Authorization can provide intent-scoped authorization to protect multi-agent systems from compromised or malicious agents, transparently and without requiring any code changes to your applications. If you'd like to learn more, check out the repository and documentation, and don't hesitate to reach out to the team with any questions.